Title: Created Out of Space. Life of a Space Engineer. Author: Created Out of Space. Inspired from the work of Dennis Taylor, Master of Science. Narrator: TTS Reader. Copyrights from Graciela Vega. Publisher: Publish Drive. Chapter 1. Publisher's Note: Created Out of Space. Life of a Space Engineer is the story of humanity's greatest journeys into space. It is told not only as history, but as a pathway for the future, where education, teamwork, and creativity allow us to transform imagination into the cosmos. From the first lessons to spacecraft traveling beyond the solar system, this book shows how engineers shape the present while opening doors to tomorrow. Chapter 2. Abstract. Aerospace engineering is more than machines. It is a culture of problem-solving, teamwork, and vision. From Apollo to Voyager, from Planck to Rosetta, and from Hayabusa to Chang'e, each mission demonstrates how human creativity, guided by physics, creates progress. The book follows these missions not only as technical achievements but as models for resilience, adaptability, and cooperation. Looking forward, it explores how reusability, artificial intelligence, and sustainability will shape the next era of exploration. It shows how aerospace engineering connects science with imagination, building a future where exploration and creation is a shared human endeavor. Chapter 3. Preface. This book is written as a journey through aerospace history and into the future. It begins with education, the universal foundation that prepares future engineers, and moves through the great missions that defined decades of exploration. Apollo, Voyager, Ulysses, Rosetta, Planck, and many more appear here not as isolated events but as steps in one continuous path. Each mission reveals not only technical breakthroughs, but also the human values behind them: adaptability, curiosity, creativity, and teamwork. By linking science with imagination, aerospace engineers transform challenges into discoveries. This book also looks ahead, showing how new technologies such as reusable rockets, AI-driven spacecraft, and sustainable systems will carry exploration further than ever before. The story is written for everyone: students, engineers, dreamers, and citizens, because the lessons of space exploration apply to all of us. They teach how to work together across cultures, how to innovate under constraints, and how to imagine futures worth building. In this way, aerospace engineering becomes more than a profession. It becomes a universal method for solving problems and creating opportunities. Chapter 4. Foundations, Education and First Steps. Every journey in aerospace engineering begins with education. Mathematics, physics, and engineering provide the universal language that allows future engineers to understand nature's laws and design within them. Across the world, classrooms and laboratories are the first launch pads of exploration. Education is not limited to theory. The transition from study to practice comes through internships, apprenticeships, and junior roles in industry. In small companies, young engineers learn agility, taking on multiple roles and gaining broad exposure to design and testing. In large organizations, they experience continuity, discipline, and the scale of international projects. Both environments teach adaptability, problem-solving, and the importance of communication. The foundation stage also builds technical literacy. Students learn how to apply Newton's laws to rockets, thermodynamics to engines, and electronics to communication systems. They are introduced to computer-aided design, simulation, and coding, tools that will accompany them throughout their careers. Most importantly, they learn to connect equations with reality, to see how theory becomes hardware. Beyond technical skills, the early years cultivate curiosity and resilience. Assignments, projects, and early failures teach that mistakes are part of progress. Aerospace work demands adaptability, patience, and creativity. Every problem has multiple solutions, but only those consistent with physics will succeed. Learning to test, to revise, and to adapt becomes as valuable as mastering formulas. This first chapter shows that education and first steps are the true launch sequence of an engineer's career. They prepare individuals to move from classrooms to spacecraft, from theory to missions, and from ambition to achievement. With these foundations, the path opens toward the great milestones of exploration that follow. Chapter 5: Apollo, the First Leap. The Apollo program of the 1960s and early 1970s was far more than a race to the moon. It was a demonstration of how aerospace engineering, when applied with discipline and creativity, can solve challenges that seemed impossible only a decade before. At its core, Apollo was an engineering system of unprecedented complexity. It required the design and integration of 3 spacecraft: the command module for crew control, the service module for propulsion and life support, and the lunar module for descent and ascent from the moon. Each component had to function independently and as part of a larger architecture, teaching engineers the essence of systems integration. The most visible symbol of Apollo was the Saturn V rocket, a machine of 110 meters in height and 3,000 tons at liftoff. The first stage, SIC, burned kerosene and liquid oxygen through 5 F1 engines, each producing 6.7 million newtons of thrust. Designing combustion stability for such engines was itself an engineering trial. Oscillations could tear the motor apart in milliseconds. Engineers used high-speed photography, acoustic chambers, and thousands of test firings to tame this beast of fire and metal. The second and third stages shifted to liquid hydrogen, an extremely efficient but extremely difficult propellant. Hydrogen leaks through microscopic pores, embrittles metals, and boils at 20 Kelvin. Engineers had to invent new insulation foams, welding techniques, and tank structures to store and control it. This was not only rocket engineering, but the birth of cryogenic systems engineering, which would later be essential for missions like Planck and James Webb. Inside the spacecraft, the guidance and navigation system represented another revolution. It contained one of the world's first digital computers, the Apollo Guidance Computer, AGC. Its memory was woven by hand, with wires threaded through magnetic cores, producing software that could not be erased in flight. Engineers had to learn not only how to write code for limited capacity, but also how to trust digital logic under real mission conditions. When Apollo 11's computer displayed 1202 alarms on descent, it was the discipline of training and confidence in redundancy that allowed the landing to continue. Human life support was another technical frontier. The suits needed to be both flexible and airtight, shielding astronauts from vacuum, radiation, and extreme temperatures. The portable life support system carried oxygen, cooling water, co-scrubbers, and power in a backpack weighing 25 kilograms, yet it had to be reliable for hours of independent use. Each element required engineering down to the smallest valve, as human safety depended on tolerances measured in fractions of millimeters. Apollo also depended on global communications and tracking. The Deep Space Network and a fleet of tracking ships formed a planetary infrastructure, proving that spaceflight is not only about rockets, but about worldwide coordination of antennas, timing, and signal processing. Every transmission, telemetry, biomedical data, voice, had to be synchronized across continents. This need for precision timekeeping accelerated advances in atomic clocks, a foundation of today's GPS and satellite navigation. The lessons for engineers were profound. Apollo showed that solving one problem often creates another. Lightweight structures vibrated, new fuels corroded materials, software revealed unexpected logic paths. What mattered was not perfection in isolation, but the ability to integrate across disciplines: structures, propulsion, avionics, thermal control, human factors. Young engineers entering Apollo learned to balance detail with system perspective, a skill that defines aerospace work to this day. Chapter 6: Voyager, the longest journey. Launched in 1977, the twin spacecraft Voyager 1 and Voyager 2 became humanity's longest and most enduring mission. They were designed for a planetary grand tour, using gravity assists to visit Jupiter, Saturn, Uranus, and Neptune in a single sequence. The mission pushed the limits of spacecraft design, navigation, and communication, and its lessons continue to guide engineers today. At the heart of Voyager was the challenge of power generation far from the Sun. Solar panels were impractical, so engineers turned to radioisotope thermoelectric generators, RTGs, which converted heat from decaying plutonium-238 into electricity. Each RTG produced about 470 watts at launch, steadily declining over decades, forcing the team to carefully manage power distribution as instruments aged. This was a masterclass in power budgeting and redundancy, ensuring that critical systems could continue even as energy faded. Communications presented another frontier. By the time Voyager reached Neptune, its signal was 20 billion times weaker than the power of a watch battery. To detect this whisper across interplanetary distances, NASA relied on the Deep Space Network, DSN, a worldwide array of giant antennas in California, Spain, and Australia. Engineers refined high-gain antennas, modulation techniques, and error-correcting codes to squeeze every bit of data from the void. This work not only enabled Voyager, but also laid the groundwork for interplanetary internet concepts and today's standards of deep space communications. Voyager's instrument payload was a scientific orchestra. Imaging cameras captured volcanic eruptions on Io and the delicate rings of Saturn. Magnetometers measured the vast magnetic fields of Jupiter and Neptune, revealing complex interactions with their moons and atmospheres. Plasma detectors mapped the solar wind, and cosmic ray instruments traced particles from beyond the solar system. Each instrument required thermal stability, electromagnetic shielding, and precise pointing, challenges that taught engineers how to protect sensitive sensors in hostile environments. Navigation demanded extraordinary precision. To fly by multiple planets separated by billions of kilometers, Voyager relied on gravity-assist trajectories, a technique where spacecraft steal momentum from a planet's motion to accelerate. This required exact calculations in Newtonian mechanics and constant updates from tracking stations. Small thrusters, burning hydrazine, executed corrections measured in fractions of degrees, keeping the spacecraft aligned for each planetary encounter. It was a living demonstration of orbital mechanics applied at cosmic scale. Perhaps the most symbolic element was the golden record. A phonograph disc, etched with sounds, music, and images of Earth, it represented not engineering necessity but engineering philosophy. That exploration is also communication of culture. Designing a record that could survive billions of years in interstellar space required materials science, encoding methods, and protective housings tested for radiation and micrometeoroids. It was both a technical artifact and a human message in a bottle. Voyager's endurance is its greatest lesson. More than 4 decades after launch, with power dwindling and instruments shutting down, the spacecraft still transmit from interstellar space. For engineers, this is proof that careful design, redundancy, and conservative operations can create machines that outlast generations. Young engineers continue to study Voyager's mission operations, learning how to extend hardware beyond its predicted life. In the story of aerospace engineering, Voyager represents patience, vision, and durability. It showed that missions are not only about first steps but also about persistence over decades. Voyager taught that when engineers design not just for success but for survival, their creations can become part of humanity's permanent voice in the cosmos. Chapter 7, Spacelab and the Shuttle Era. The 1980s marked a new phase in space exploration. The era of the reusable space shuttle and its European companion module, Spacelab. This period represented a shift from one-off exploration to routine access to low Earth orbit, where experiments, industry, and international cooperation could grow together. The Space Shuttle itself was an engineering contradiction, part rocket, part airplane, part laboratory. It was designed to be reusable, carrying astronauts and payloads into orbit and returning them safely to Earth. Its thermal protection system, made up of more than 24,000 fragile ceramic tiles, had to survive re-entry temperatures hotter than molten lava. Every tile was unique, coded to a specific position, and had to be inspected after each mission, teaching engineers about maintenance cycles in reusable spacecraft. Attached to the shuttle was Spacelab, developed by the European Space Agency. It was a pressurized laboratory module that fit inside the shuttle's payload bay, transforming it into a fully equipped orbital research center. For European engineers, this project was a milestone. It required mastering life support systems, environmental controls, and interfaces with American hardware. Spacelab showed that international collaboration could create a spacecraft as a true modular laboratory in orbit. Inside Spacelab, scientists performed experiments in microgravity across physics, biology, and materials science. Fluids behaved differently without gravity, leading to discoveries in capillary action and thermal convection. Biological studies tested how plants and human cells adapted to weightlessness, providing early data for long-duration missions. Materials engineers melted alloys and grew crystals without the distortions of gravity, paving the way for industrial applications. Each experiment demanded miniaturized instruments, automated controls, and real-time telemetry, creating new fields in space laboratory engineering. The shuttle era also advanced payload integration. Every mission carried satellites, probes, or telescopes into orbit, often alongside crew and Spacelab. This required careful design of mounting structures, release mechanisms, and vibration isolation systems to protect sensitive payloads during launch. Engineers learned how to treat the shuttle as a multi-mission platform, adapting its bay for telescopes, defense satellites, and even components of the International Space Station. Culturally, Spacelab represented a turning point. For the first time, European astronauts flew regularly aboard American missions, bridging training programs, languages, and engineering philosophies. This collaboration required standardization of connectors, software protocols, and safety rules, lessons that became the backbone of later programs like the ISS. It was an exercise not only in aerospace engineering, but in international systems engineering, where politics and culture were as important as materials and electronics. The Shuttle and Spacelab era also revealed the limits of reusability. Every orbiter required thousands of hours of inspection and refurbishment between flights. This showed engineers that reusability is not only about surviving reentry but about designing for rapid turnaround with minimal maintenance. It was a hard lesson that still informs companies building reusable rockets today. Despite challenges, Spacelab and the shuttle left a legacy of routine orbital engineering. They trained engineers to integrate laboratories, payloads, and human crews in one vehicle, a skill that would later prove essential for constructing and operating the International Space Station. For young engineers, the shuttle era was a school in versatility, learning to design for science, industry, and exploration all at once. In the timeline of aerospace engineering, Spacelab and the shuttle symbolized international partnership and modular design. They taught that spaceflight is not just about reaching new worlds but about building sustainable platforms in orbit. The Shuttle and Spacelab showed that when engineers from different nations collaborate, they can create vehicles that embody the shared ambitions of humanity. In the end, Apollo's leap was not only to the moon. It was a leap in systems engineering as a philosophy, the idea that thousands of independent parts and people can work in harmony when guided by common laws of physics and disciplined creativity. The moon rocks returned were valuable, but even more valuable was the generation of engineers forged in the fire of impossible deadlines, who carried their skills into future missions. Chapter 8: Ulysses. Patience and the Sun's Poles. The Ulysses mission, launched in 1990, was designed to do something no spacecraft had ever attempted: study the poles of the Sun. To achieve this, engineers had to rethink trajectories, instruments, and communications for a mission that would orbit at a steep angle to the ecliptic plane. It was a lesson in patience, resilience, and precision, both in design and operations. The journey began with a challenge of orbital mechanics. No rocket on Earth could directly send a spacecraft out of the ecliptic plane to high solar latitudes. Instead, Ulysses used a gravity assist from Jupiter, flying close enough to the giant planet to bend its trajectory over the Sun's poles. This required exact navigation, as a small error at Jupiter would ruin the entire mission geometry. The maneuver demonstrated how engineers use celestial mechanics not just for speed, but for changing orbital inclination in ways rockets alone cannot achieve. Power generation was another critical issue. Because Ulysses would fly far from the Sun, solar panels were impossible. The spacecraft relied on a single radioisotope thermoelectric generator, RTG, using plutonium-238 to provide steady electrical power. This required shielding, thermal controls, and strict safety standards at launch, teaching engineers how to operate long-term missions with nuclear power in deep space. The payload of instruments was designed to probe the Sun's environment in multiple ways. Magnetometers mapped the solar magnetic field, while plasma detectors measured the flow of charged particles from the solar wind. Cosmic ray detectors studied how interstellar particles were modulated by solar activity. Dust detectors traced interplanetary particles crossing the solar system. Each instrument required careful calibration, as Ulysses had to operate in regions where temperatures swung from extreme cold near Jupiter to solar heating at perihelion. Communications again relied on the Deep Space Network, DSN. Because Ulysses traveled out of the ecliptic plane, antenna coverage had to be managed across multiple hemispheres. Data rates were often low, forcing engineers to design data compression and priority scheduling, deciding which instrument results to send first. This trained engineers in balancing limited bandwidth with maximum science return, a lesson still vital for missions at the edge of the solar system. The mission also demanded resilience in operations. It had to postpone it for years after the loss of our launch vehicle Challenger. That loss was an example of a big mistake by NASA to launch in low temperatures where the solid rocket booster seals were not qualified. The upper stage had to be changed from a liquid-fueled Atlas Centaur to a solid rocket payload assist module, PAM, after restrictions introduced by the loss of Challenger. It also had to change the whole ground segment computers from ModComp to RSX-11 because of foreseen obsolescence due to years of launch delay. Once in flight, it faced multiple thermal and mechanical stresses, yet the spacecraft exceeded its design lifetime by more than a decade. Patience became as important as engineering, as teams had to sustain expertise across generations of scientists and controllers. Ulysses revealed the three-dimensional nature of the solar wind. It showed that high-speed solar wind streams flow from the poles during quiet solar periods, while complex structures emerge during maximum activity. Its discoveries changed models of heliophysics and improved space weather prediction, protecting satellites and astronauts closer to Earth. The mission proved that understanding the Sun requires not only staring at it from Earth, but circling it in dimensions unreachable by traditional orbits. For aerospace engineers, Ulysses symbolized precision, nuclear power operations, and mission endurance. It showed that patience in planning and resilience in execution are as important as hardware design. Above all, it proved that with creative use of gravity and careful resource management, even small spacecraft can achieve discoveries far beyond their size. Chapter 9: Earth from Space – Satellites for Society. If Apollo and Voyager were symbols of exploration, Earth observation satellites became symbols of service. From weather prediction to disaster monitoring, satellites showed how aerospace engineering could transform daily life on Earth. These missions required innovations in sensors, data transmission, and long-term satellite operations, creating a new field of engineering for society. The Meteosat second generation (MSG) satellites, operated by EUMETSAT, provided continuous images of Europe, Africa, and the Atlantic every 15 minutes. This capability demanded large rotating platforms with spin stabilization, allowing scanning radiometers to sweep Earth's disk with precision. Engineers had to master thermal balance, as one side faced the Sun while the other stared into space, and power systems had to operate continuously for more than a decade. The result was real-time weather forecasting that saved lives in aviation, shipping, and agriculture. Complementing MSG was the EPS METOP program, polar orbiting satellites that circled Earth from pole to pole. Unlike geostationary platforms, polar orbiters provided global coverage, scanning every point on Earth twice per day. They carried instruments like microwave sounders, infrared spectrometers, and ozone monitors, each demanding careful calibration and long-term stability. These systems turned raw radiance into profiles of temperature, humidity, and chemical composition, feeding the numerical weather models that underpin modern forecasting. Building Earth observation satellites required new approaches to engineering reliability. Unlike planetary probes, which send back unique science snapshots, weather satellites must operate continuously with 99.9% availability. This forced engineers to refine redundancy schemes, error detection, and automated recovery systems. Every subsystem, power, communications, attitude control, was duplicated, ensuring that failures would not compromise data delivery. The data transmission challenge was enormous. Satellites produced terabytes of raw data, far more than could be sent in real time. Engineers created on-board pre-processing and compression systems, transmitting prioritized data streams to ground stations in Europe, Antarctica, and North America. Ground segments then distributed the data to meteorological agencies worldwide within minutes, a global network of engineering as much as science. Earth observation also demanded advances in remote sensing calibration. Instruments measuring Earth's temperature or ozone had to remain accurate over decades, despite exposure to radiation and mechanical wear. Engineers built on-board calibration systems using blackbody radiators and solar diffusers, while cross-checking measurements between satellites flying years apart. This created the concept of climate data records, consistent long-term datasets that track global warming and atmospheric change. Applications extended far beyond meteorology. Earth observation satellites guided search and rescue beacons, monitored wildfires, mapped deforestation, and tracked ocean currents for shipping. They supported humanitarian responses to earthquakes, floods, and hurricanes by providing rapid imagery to relief agencies. For engineers, this meant designing systems that were not only precise but also operationally responsive, with tasking flexibility and rapid downlink options. The lesson of Earth observation missions is that aerospace engineering can be both technical and societal. Engineers learned to design not just for exploration but for service, where uptime, reliability, and global cooperation were as important as scientific discovery. In doing so, they transformed space from a distant frontier into an everyday infrastructure, woven into agriculture, transport, disaster response, and climate policy. Chapter 10: Eastern Horizons. Hayabusa, Chang'e, Chandrayaan. As the 21st century began, new nations joined the frontier of exploration. Japan, China, and India developed bold missions that showed how aerospace engineering was no longer limited to a few countries. Each program reflected unique cultural approaches, yet all shared the same discipline of physics and systems integration. Japan's Hayabusa mission, launched in 2003, aimed to collect samples from the asteroid Itokawa. This required engineering a spacecraft capable of autonomous navigation in microgravity. Asteroids are irregular, with weak gravity fields, so Hayabusa could not orbit in a traditional sense. Instead, it hovered and maneuvered using ion propulsion and laser altimeters, proving new techniques for deep space rendezvous. Its sample collection mechanism fired a projectile into the surface, capturing particles in a capsule that survived fiery re-entry to Earth. Although plagued by fuel leaks and reaction wheel failures, Hayabusa succeeded, teaching engineers how resilience and creative recovery strategies can salvage missions. China's Chang'e program demonstrated mastery of lunar exploration. From 2007 onward, orbiters, landers, and rovers expanded capabilities step by step. A landmark came with Chang'e 4, the first spacecraft to land on the far side of the Moon in 2019. Because the far side never faces Earth, direct communication was impossible. Engineers placed the Queqiao relay satellite at the Earth-Moon L2 point, a position of gravitational balance, ensuring continuous contact. This required advanced orbital mechanics, antenna design, and autonomous systems. Chang'e missions also tested robotic drills, sample return capsules, and lunar night survival systems, paving the way for human exploration. India's Chandrayaan and Mangalyaan programs showed how resourcefulness can achieve interplanetary success at low cost. Chandrayaan-1, launched in 2008, orbited the Moon with instruments that detected water ice at the poles. Its payload included spectrometers and radar supplied by international partners, proving India's ability to integrate global contributions. In 2013, the Mars orbiter mission, Mangalyaan, became the first Asian spacecraft to reach Mars orbit. Built with a modest budget, it relied on careful weight reduction, efficient trajectory planning, and extended ground testing. This mission proved that reliability and clever engineering can compensate for limited resources. These missions showed that space exploration is now a shared global endeavor. Each nation contributed not only data but also new engineering lessons, from ion propulsion to relay satellites to cost-efficient planetary flight. For young engineers, Hayabusa, Chang'e, and Chandrayaan demonstrated that ingenuity, patience, and collaboration can open frontiers once thought reserved for superpowers. Chapter 11: Planck, Harmony in the Coldest Object. The Planck satellite, launched in 2009 by the European Space Agency, was designed to map the cosmic microwave background, CMB, with unprecedented precision. It became the coldest object in space, pushing engineering into the frontiers of cryogenics, detector physics, and system stability. Its mission demonstrated how aerospace engineering can probe the deepest origins of the universe. The scientific goal was to measure tiny temperature differences, less than a millionth of a degree, in radiation left over from the Big Bang. To do this, Planck carried two main instruments: the low-frequency instrument, LFI, using radiometers, and the high-frequency instrument, HFI, using bolometers cooled to just 0.1 Kelvin. This required an elaborate chain of cryogenic coolers, including liquid helium and mechanical systems, to progressively step down the temperature. Each stage of cooling had to remain stable for years, with vibration isolation to prevent the detectors from being disturbed by their own refrigerators. The spacecraft's thermal design was as critical as its instruments. Planck was placed at the second Lagrange point, L2, 1.5 million kilometers from Earth, where the Sun, Earth, and Moon all lay in one direction. This allowed engineers to use a system of reflective shields, blocking sunlight and keeping the spacecraft permanently oriented away from heat sources. At L2, Planck could radiate heat into deep space, achieving the stability needed for ultra-sensitive measurements. The detectors themselves represented the edge of physics. Bolometers in the HFI absorbed individual photons of the microwave background, producing signals through minute changes in resistance. Electronics had to detect these changes with almost no noise, requiring shielding from cosmic rays and stray electromagnetic interference. The system taught engineers how to design ultra-low-noise electronics and integrate them into spacecraft exposed to radiation and mechanical stress. Data handling was another frontier. Planck generated continuous streams of high-precision measurements that had to be compressed and transmitted back to Earth. The Deep Space Network provided the link, but bandwidth was limited, so engineers implemented onboard data compression without losing scientific fidelity. Ground teams then processed the raw data into all-sky maps, applying algorithms that separated galactic foregrounds from the ancient cosmic signal. This process required close teamwork between aerospace engineers, physicists, and computer scientists. The mission's results were transformative. Planck provided the most detailed map of the universe's early structure, refining measurements of its age, composition, and geometry. It showed that ordinary matter makes up less than 5% of the universe, with the rest composed of dark matter and dark energy. For engineers, the achievement was not only scientific but methodological, proof that cryogenics, precision electronics, and stable orbits could be combined into one harmonious system. Planck's legacy lies in its integration of extremes. It balanced temperatures near absolute zero with constant exposure to cosmic radiation. It linked delicate detectors with robust spacecraft operations lasting years beyond design life. It embodied harmony between physics and engineering, between fragile instruments and strong spacecraft, and between scientific ambition and technical discipline. Chapter 12, Rosetta, Chasing a Comet. The Rosetta mission, launched in 2004 by the European Space Agency, was one of the most ambitious and daring projects in the history of spaceflight. Its goal was to rendezvous with Comet 67P Churyumov-Gerasimenko, escort it around the Sun, and deploy a lander onto its surface. This mission required unmatched precision in orbital mechanics, spacecraft endurance, and engineering resilience. The journey lasted more than a decade. Because no rocket could send Rosetta directly to its cometary target, engineers designed a trajectory with multiple gravity assists from Earth and Mars. Each flyby added speed and adjusted the orbit, guiding Rosetta through the inner solar system before reaching the comet in 2014. This demanded continuous navigation updates, with course corrections using small thrusters firing for seconds at a time. It was an exercise in celestial mechanics extended over years, requiring patience and flawless execution. The spacecraft itself was built for endurance. It carried large solar arrays, stretching 32 meters tip to tip, to generate power even when operating beyond Jupiter's orbit. This was the first time solar power had been used so far from the Sun, requiring ultra-efficient cells and careful orientation to capture every photon. Thermal systems had to cope with extreme variations, from deep space cold to the heat of perihelion. Every subsystem, power, communications, instruments, had to survive hibernation periods lasting years, when Rosetta was switched off to conserve energy. Rosetta carried a sophisticated suite of instruments to study the comet. Spectrometers analyzed gases released as the comet warmed, cameras mapped its surface in high resolution, and dust analyzers measured the composition of particles streaming away. These instruments required shielding from contamination by the comet's own dust and gases, forcing engineers to design shutters and protective covers that could be deployed multiple times. Rosetta was not just a spacecraft but a mobile laboratory, capable of operating in one of the harshest and most unpredictable environments in the solar system. The most daring part of the mission was the deployment of the Philae lander. Landing on a comet, only a few kilometers across with microgravity conditions, was unlike anything attempted before. Philae was equipped with harpoons to anchor itself, ice screws in its legs, and thrusters to hold it down. When it touched the surface in November 2014, the anchoring systems failed, and Philae bounced several times before coming to rest in shadow. Even so, it transmitted data from the comet's surface, analyzing organic molecules and surface hardness. This partial success was a reminder that in frontier engineering, not all risks can be eliminated, but even partial victories yield discoveries. Communications for Rosetta pushed the limits of the deep space network. At distances beyond 500 million kilometers, signals took nearly half an hour to travel one way. Engineers relied on high-gain antennas, redundant transmitters, and precise timing to maintain contact through solar conjunctions and spacecraft hibernation cycles. The ability to command and receive science data over such distances was itself a triumph of radio engineering. Rosetta revealed a world of surprises. The comet was not a simple ball of ice but a complex, double-lobed structure, shaped like a rubber duck. Jets of gas and dust erupted from fissures, reshaping the surface as the comet approached the Sun. Philae's instruments found organic compounds, supporting theories that comets may have delivered the building blocks of life to Earth. For engineers, each unexpected feature meant adjusting operations in real time, proof that adaptability is as critical as planning. Rosetta's end came in 2016, when controllers commanded it to descend onto the comet's surface, completing the mission. Rather than leaving a silent satellite in orbit, they chose a controlled impact, gathering data until the last moment. It was both a scientific and symbolic act, engineers and scientists accompanying their spacecraft to the very end. For aerospace engineers, Rosetta was a masterpiece of endurance, precision, and daring. It showed how long-term missions can combine navigation, autonomy, and resilience to achieve the impossible. Rosetta proved that with creativity, patience, and international teamwork, humanity can reach, land on, and study objects that once seemed forever beyond our grasp. Chapter 13: The Engineer's Toolkit – Lessons from Decades. After decades of missions, from Apollo to Voyager, from Ulysses to Rosetta, aerospace engineers have built a toolkit of methods and disciplines that apply across every project. This toolkit is not just hardware and software, but a philosophy of how to design, test, and operate under the unforgiving laws of physics. The first tool is systems engineering. Spacecraft are complex machines where propulsion, power, thermal control, avionics, and payloads must all work in harmony. Systems engineering teaches how to define requirements, trace them to subsystems, and verify them through analysis and testing. It emphasizes the balance between performance, cost, schedule, and risk, a balance that every mission must navigate. This discipline is as much about communication as it is about design, ensuring that every engineer understands how their work fits into the whole. The second tool is testing and verification. Because repairs in space are nearly impossible, every component must be validated on Earth. This includes vibration tests to simulate launch, thermal vacuum tests to reproduce space conditions, and electromagnetic compatibility tests to prevent interference. Often, testing reveals flaws that design reviews missed, showing why aerospace engineering depends on iteration and resilience. Testing is not failure but discovery, and discovery is part of engineering progress. The third tool is redundancy and fault tolerance. Every mission faces uncertainty. Sensors can fail, valves can jam, software can crash. Engineers design backup systems, cross-strapped electronics, and autonomous saving modes to ensure survival. The lesson from Voyager and Ulysses is that with smart redundancy, spacecraft can last decades beyond their design life. Redundancy is not excess, it is the price of resilience in the void. Another tool is communication and documentation. Large missions involve thousands of people, often across continents. Clear specifications, version control, and open channels of communication prevent small errors from cascading into mission failure. The Shuttle and Spacelab era proved that international collaboration requires not only compatible hardware, but compatible languages, standards, and expectations. In aerospace, good documentation is as critical as good design. The toolkit also includes innovation under constraint. Budgets, schedules, and payload limits force creativity. India's Mars orbiter showed how careful weight reduction and efficient trajectories could achieve interplanetary flight at a fraction of traditional costs. Hayabusa showed how small spacecraft, even with failures, could return asteroid samples through ingenuity. Constraints sharpen the engineer's mind, turning obstacles into opportunities for invention. Finally, the engineer's toolkit is incomplete without teamwork and adaptability. Every mission has faced surprises: Apollo's alarms, Rosetta's bouncing lander, Planck's cryogenic challenges. What saved them was not only hardware but human collaboration, the ability to analyze, decide, and adapt together. This human factor is why aerospace engineering remains as much about people as about machines. When engineers combine discipline with creativity, missions succeed even against uncertainty. The lessons of decades form a toolkit for the future. They show that aerospace engineering is not a collection of isolated techniques, but a unified method of solving. It is a culture of precision, resilience, and imagination, built one mission at a time. And it reminds us that while spacecraft may leave Earth, the skills and teamwork that built them remain here, ready for the next challenge. Chapter 13: The Engineer's Toolkit – Lessons from Decades. After decades of missions, from Apollo to Voyager, from Ulysses to Rosetta, aerospace engineers have built a toolkit of methods and disciplines that apply across every project. This toolkit is not just hardware and software, but a philosophy of how to design, test, and operate under the unforgiving laws of physics. The first tool is systems engineering. Spacecraft are complex machines where propulsion, power, thermal control, avionics, and payloads must all work in harmony. Systems engineering teaches how to define requirements, trace them to subsystems, and verify them through analysis and testing. It emphasizes the balance between performance, cost, schedule, and risk, a balance that every mission must navigate. This discipline is as much about communication as it is about design, ensuring that every engineer understands how their work fits into the whole. The second tool is testing and verification. Because repairs in space are nearly impossible, every component must be validated on Earth. This includes vibration tests to simulate launch, thermal vacuum tests to reproduce space conditions, and electromagnetic compatibility tests to prevent interference. Often, testing reveals flaws that design reviews missed, showing why aerospace engineering depends on iteration and resilience. Testing is not failure but discovery, and discovery is part of engineering progress. The third tool is redundancy and fault tolerance. Every mission faces uncertainty. Sensors can fail, valves can jam, software can crash. Engineers design backup systems, cross-strapped electronics, and autonomous saving modes to ensure survival. The lesson from Voyager and Ulysses is that with smart redundancy, spacecraft can last decades beyond their design life. Redundancy is not excess, it is the price of resilience in the void. Another tool is communication and documentation. Large missions involve thousands of people, often across continents. Clear specifications, version control, and open channels of communication prevent small errors from cascading into mission failure. The Shuttle and Spacelab era proved that international collaboration requires not only compatible hardware, but compatible languages, standards, and expectations. In aerospace, good documentation is as critical as good design. The toolkit also includes innovation under constraint. Budgets, schedules, and payload limits force creativity. India's Mars orbiter showed how careful weight reduction and efficient trajectories could achieve interplanetary flight at a fraction of traditional costs. Hayabusa showed how small spacecraft, even with failures, could return asteroid samples through ingenuity. Constraints sharpen the engineer's mind, turning obstacles into opportunities for invention. Finally, the engineer's toolkit is incomplete without teamwork and adaptability. Every mission has faced surprises: Apollo's alarms, Rosetta's bouncing lander, Planck's cryogenic challenges. What saved them was not only hardware but human collaboration, the ability to analyze, decide, and adapt together. This human factor is why aerospace engineering remains as much about people as about machines. When engineers combine discipline with creativity, missions succeed even against uncertainty. The lessons of decades form a toolkit for the future. They show that aerospace engineering is not a collection of isolated techniques, but a unified method of solving. It is a culture of precision, resilience, and imagination, built one mission at a time. And it reminds us that while spacecraft may leave Earth, the skills and teamwork that built them remain here, ready for the next challenge. Chapter 14: The Future: Reusability, AI, Sustainability. The future of aerospace engineering lies at the intersection of innovation and responsibility. Reusability, artificial intelligence, and sustainability are transforming how missions are designed, launched, and operated. They represent not only new technologies but a new philosophy, that exploration must be continuous, efficient, and mindful of its impact. Reusability has already reshaped launch systems. Rockets like SpaceX's Falcon 9 demonstrated that first stages can return to Earth, land vertically, and fly again. This required advances in propulsion throttling, guidance algorithms, and structural materials able to survive multiple flights. Reusability reduces cost per launch, but also changes design priorities. Engines must be designed for hundreds of ignitions, and thermal protection must withstand repeated heating cycles. Other nations, from China to India, are now developing their own reusable systems, ensuring this approach will dominate the coming decades. Artificial intelligence, AI, is the next transformative tool. Future spacecraft will rely on autonomous decision-making, allowing them to adapt to failures, adjust trajectories, and prioritize science without waiting for ground commands. Machine learning can process images on board, selecting the most valuable data to transmit when bandwidth is limited. AI also assists in design. Engineers now use generative algorithms to optimize structures, thermal systems, and communication networks beyond human intuition. This is not about replacing humans but amplifying creativity, freeing engineers to focus on high-level strategy while AI handles repetitive calculations. Sustainability is a growing imperative. The space environment is filling with debris, dead satellites, spent rocket stages, and fragments from collisions. Engineers are developing active debris removal technologies, such as robotic arms, nets, and harpoons to capture and deorbit space junk. Satellites are increasingly designed with end-of-life plans, including propulsion for controlled reentry, orbits that decay safely. Materials are being selected for minimal contamination and recyclability, reducing the ecological footprint of launches. Future missions will also emphasize sustainable energy and propulsion. Solar electric propulsion, using ion or Hall effect thrusters, provides efficient long-duration thrust, already proven on missions like Dawn. Nuclear thermal propulsion is under study for deep space human missions, promising faster transit to Mars. At the same time, green propellants are replacing toxic hydrazine, making ground operations safer and reducing environmental hazards. Each innovation reflects a growing awareness that exploration cannot ignore its consequences. The future also includes international and commercial collaboration. Mega constellations of satellites for communication and Earth observation are being built by private industry, requiring coordination on spectrum, orbital slots, and collision avoidance. Governments and companies will need shared standards to ensure safety and equity. The same is true for exploration. Artemis, Lunar Gateway, and Mars missions will depend on multiple nations contributing modules, spacecraft, and logistics. Engineering in the future will be as much about cooperation and standards as about materials and propulsion. For aerospace engineers, the path ahead is both challenging and inspiring. They must design rockets that fly again and again, spacecraft that think for themselves, and missions that preserve both Earth and space environments. The Future Toolkit combines reusability, AI, and sustainability into a coherent approach. Efficiency, autonomy, and responsibility. It is a reminder that the frontier of space is inseparable from the stewardship of Earth. Chapter 15: Harmony on Earth and Beyond. The greatest lesson of aerospace engineering is found in single missions and across missions, in the harmony between people, machines, and the laws of physics. From Apollo's giant rockets to Planck's cryogenic detectors, every success has been the result of collaboration across cultures and disciplines. Aerospace engineering shows that when humans align their creativity with the universal order of nature, progress becomes inevitable. Harmony begins with teamwork. Every spacecraft represents the labor of thousands of engineers, technicians, scientists, and managers, each solving at different scales. It is the integration of these diverse contributions that allows each part and the whole mission to succeed. Whether through multinational programs like Spacelab or partnerships between agencies on Chandrayaan, harmony in teamwork transforms ambition into achievement. Harmony also exists between discipline and creativity. Physics is uncompromising. Rockets obey Newton's laws, electronics fail under radiation, and cryogenics demand absolute precision. Yet within these constraints, engineers find freedom to innovate, inventing new algorithms, new materials, and new architectures. This balance between rigor and imagination is what makes aerospace engineering not only technical but also profound. Artificial intelligence now joins this harmony. AI supports engineers in design, testing, and mission operations, augmenting decision-making with speed and breadth of analysis. It is a partner, not a replacement, allowing humans to dream while machines handle complexity. Together, humans and AI embody a new form of teamwork, one that mirrors the collaboration of cultures in past missions. Harmony is also about responsibility to Earth. Space missions remind us that our planet is fragile. Earth observation satellites show us storms, fires, and melting ice, making clear that engineering must serve not only exploration but preservation. The harmony between exploration and care is essential to reach the stars while protecting our current home, Earth. Finally, harmony lies in the shared destiny of humanity. From the golden record on Voyager to the global teams behind Rosetta, every mission carries a message: that exploration belongs to all people. One day, as engineers and citizens, we may expand into the interstellar system, carrying not only technology but values of cooperation and respect. The cosmos invites us not just to conquer, but to participate in its order with humility and creativity. In space engineering, harmony is not a metaphor but a practice. It is found in precise orbits, synchronized antennas, aligned teams, and balanced systems. When we live as space engineers, guided by harmony, we do more than build spacecraft, we build futures worthy of the universe itself. Chapter 16. Conclusion. The journey of space engineering is the story of how humanity transforms dreams into reality. From the moon landings to the exploration of comets and the mapping of the cosmic background, each mission proves that what seems impossible today can become routine tomorrow. Every spacecraft is a monument not only to technology, but to human imagination and cooperation. The future holds even greater horizons. Reusability, artificial intelligence, and sustainable propulsion will make spaceflight more accessible, reliable, and responsible. The engineering of tomorrow will not only solve technical problems, but also design new ways of humanity to live and work beyond Earth. Aerospace engineering shows how science fiction becomes science fact. As the book Created Out of Space, From the Big Bang to Eternity explores, creativity, science, and ethics are partners in shaping new futures, linking inspiration to action. Missions succeed when people from different cultures work together, when discipline and creativity reinforce one another, and when ambition aligns with the laws of physics. This harmony is not abstract, it is found in orbits precisely calculated, antennas aligned across continents, and teamwork that bridges nations. In learning to cooperate for space, we also learn how to cooperate better on Earth. The cosmos challenges us to think bigger and to act with courage and caution. By designing for resilience, innovation, and sustainability, aerospace engineers are building the foundations of a future where exploration is open to all. One day, we will all live as space engineers, adapting to and creating with the cosmos, in harmony with each other and the laws of physics.